very envious of your sunlight level there right now, and very long days. I love Alaska. And your talk, Jerome's talk, is going to be on excavation and mobility of lunar regolith. So take it away, Jerome.
Thanks. I'm waiting for it to show up on screen. Is my webcam connected or working?
Yeah, we don't see you yet.
Jerome, you can go ahead and start your webcam.
I guess I'm not sure how I do that.
In the upper left corner of the Connect session should be a gray button that says Start My Webcam.
Okay, I see that.
Excellent. You might have to hit Allow.
Okay.
Great, we see you now.
So I'm going to talk about lunar regolith mobility and excavation modeling and give kind of a final report of the work we've done as part of the scientific and exploration potential of the Lunar Poles project. As you can see, quite a few people have contributed to this work, both in terms of numerical modeling, conducting experiments, and also analysis. So what we're trying to accomplish is to solve the problem that the effects of different gravity, soil types, and physical processes on the moon, asteroids, and other planets make it impossible to accurately model or predict machine performance from Earth-based tests alone or from traditional models. And our goal has been to develop a physical discrete element method model titled Controlled Objects, Unbounded Particles Interaction, or CUPI, that non-DEM specialists can use to solve a variety of problems in space sciences and engineering related to the moon. Things such as excavation mobility, crater weathering, volatile migration, and other problems. In a physical DEM, we try to incorporate the microscale physically based properties and process algorithms that produce emergent macroscale behaviors. That is, we try to create a virtual experiment. In the DEM approach, we represent a granular material by its individual components and assign properties to those components to try and make them be a better representation of the material itself, things such as size and size distribution and the like. This drum is supposed to be an actual video. Let's see if that... There's something I have to do special to get that to run.
Jerome, they're going to be static JPEGs. There won't be a video.
Okay, is that true with all of them?
Yeah.
Okay.
I
So
should note.
I must have missed that. Okay, so the features of a physical DEM are that we try and incorporate improved realism of the digital representation of regolith properties and processes. Again, including things such as particle shape and size distributions, gravity, elastic modulus, and other features that may be important. And on the right, we're showing some of these methods that we're trying to accomplish. And another aspect of physical DEM is the need to conduct physical tests and compare those tests to the DEM simulations, both to guide the direction of the DEM development and determine which physical properties are and processes are the important ones to incorporate. One of the most significant problems to deal with is to try and get the correct particle shapes within a DEM. And when DEM was first, discrete element methods were first developed, spheres were the predominant method of particle shape that was used. And as it was recognized that more complicated particle shapes were needed, they increased it to 3-sphere particles, 4-sphere particles, and other more complicated shapes. In the slide that I'm showing here now, we've developed a technique where we use regular polyhedral geometries and overlap them to achieve whatever particle shape we want. And in the case here, you can see in the far right a representation of JSC1A in the concave representative of JC1A under G, which is a representation of the CT scan shown on the far right. You can learn more about this technique by looking at the poster by Anton Kolchevsky in the current symposium. This next slide shows the importance of considering particle shape in doing discrete element simulation. In this slide, we show the relative density range that one is able to achieve through experiment in the upper range. So we're plotting here the relative density of a packing of granular material. And for this experimental range, if you look off to the left, you'll see some images of CT scanned particles that were representative of that soil type. And then in the middle range, the 3-sphere particles show the relative density range that can be achieved with the simple 3-sphere DEM particle. And then in the bottom range, which actually exceeds the range of the experimental relative densities that are able to be achieved, this was accomplished by constructing digital representations of the CT scans of the experimental soils and then using those. So you can see that it is really important to consider particle shape. Another aspect of soils that's important to consider is its particle size distribution. And here we show a representative log normal particle size distribution, identifying both the maximum particle size and the minimum particle size. The width of this distribution is something that it's uncertain as to how much of the particle size distribution in the real soil you have to retain in your simulation in order to achieve an accurate result. For regolith on the moon or even soils on Earth, it's very difficult to construct a complete particle size distribution simply because of the size range of the particles and the number of particles that would be necessary to do that. So we did an investigation to see how much of that particle size distribution needed to be retained. And we did that by doing gravity settling experiments in a DEM using particle size distributions of different widths, which are defined by the ratio of the maximum particle size to the minimum particle size. And what you find in these curves are that when you increase the width ratio from a factor of 1 to 10, you do see that the bulk density increases, which indicates that the particle size distribution has an important effect during that range. When you increase it beyond 10, it doesn't seem to have much effect. So this can be, if we understand that to be correct, then that means we can focus our computational power on other aspects of a model rather than trying to incorporate the full range of particle size distribution. Now, unfortunately, since these are all JPEGs, they were movies at one time, I can't really show you the comparison, but this is an example of the experiment that we did on the right-hand side of Mars rover wheel digging, and then on the left-hand side was the DEM simulation of that. And were I able to show this to you, you would see quite a good similarity in the geometric representation of what was going on in terms of the digging process and how the soils were displaced and built up. But the important thing in terms of a DEM, of a physical DEM, is how well you can quantitatively match the experiment with the simulation. And in this slide, we show the torques and sinkage of the experiment, which is given in black, and the simulation, which is given in red. In this simulation, we used sharp polyhedroid grains and a fairly large size distribution in order to try and achieve as close a match as we could. We had done similar simulations of this problem using spheres and using ellipsoid particles in which it was not possible to get a very close match to the results. And if we further increased the fidelity of the DEM by actually using specific particle shapes that could be associated with the regolith that was used in the experiment and increasing the particle size distribution range, I suspect we could further improve our agreement. Another simulation that we did was of a Mars exploration rover scuff test, in which the Mars exploration locks 5 of its wheels and turns a single wheel in a partial rotation. to dig out a small depression, and in the process measures the sinkage and the torque involved with that. The lower picture is a DEM, or is a representation of the DEM simulation of that. And the objective is to try and estimate Mars in situ soil properties. In this table, we show Mars exploration rover scuff test results for Sol 371 and for Sol 879, and then a series of DEM simulations using different particle shapes, polyellipsoid 1 and polyellipsoid 2, and then 2 polyhedra types. The tests that I want to draw your attention to are highlighted in orange for the Mars exploration rover scuff test on Sol 879. You see that the sinkage was 25 millimeters with a torque of about 12 Newton meters. And if you go through the DEM simulations of the different particle size, you see that we're not able to match the sinkage very well for all except for the polyhedra, which at the bottom orange row shows a sinkage of 26 and a wheel torque of about 7. The difference in wheel torque between the measured and the simulation is something that we're not too concerned about because of the high uncertainty in trying to determine torque from actual wheels on Mars, since those are estimated by measuring current to the motors as they're turning. And in this particular simulation, we estimated a friction angle for the soil of 40 degrees compared to a range of between 30 and 37 that are determined from other means, friction angle being a measure of the soil mechanical strength. So again, this was meant to be a video, but on the left is an experiment that was conducted of a scoop in JSC-1A, both percussive and static scoop measurements were made, and then on the right, the DEM simulation of that. And again, were you able to see the video, you see the geometric progression was quite similar. And in both of these cases, the static experiment resulted in higher forces than the percussive experiment, and we were able to replicate that with the discrete element modeling as well. This was also to be a video, and here this was a representation of asteroid formation where we took separate spheres and assigned them a slight velocity and then let it go with self-gravity between the particles. And the particles were agglomerated themselves into a single object, asteroid object, and through that process a collision also created a moon. So this was a demonstration of the ability to represent self-gravity. And this last, again, was a video demonstrating control functions where the blue ball represented an asteroid object, and the net with the 4 objects on its corners was a capture mechanism with control rockets that captured the device and flew off with it. A big part of what we've been trying to do, along with adding physical features to the DEM, is also to increase its computational capabilities. And you can see here that from when we started the process, we're at we increased the computational capabilities by over 100 times, and we're now at version 0.6 beyond here, continuing that development.
Just a couple of minutes left, Jerome.
So in conclusion, in the 4 years, we have in fact constructed a physical DEM modeling capability that can simulate important excavation and mobility models that can't be solved in other ways, and at higher accuracy than qualitative DEM approaches. And I really want to emphasize this point because you can construct similar simulations to what we've been doing using spherical particles or less representative physical processes, and get pictures that appear similar to the item that you're trying to simulate. But then if you start trying to make quantitative comparisons to them, you'll find that there's not much realism. And the list that I have underneath this conclusion shows the kinds of simulations and tests that we've done to validate the model. It's wheel digging, percussive and static excavation tracks, those are the technical strength tests, and cone penetrometer strength tests. So CuPy is a multiprocessor discrete element model, and it can run on laptops, desktops, and supercomputers. And we're continuing to improve its capabilities and physical properties and computational speed. And we're now in the process of looking at other applications beyond just the excavation and mobility application that this particular project was designed to deal with. And this is a list of future directions of how we're heading as we move on with development. Thank you.
Thanks very much, Jerry. I have to say, it continues to amaze me the kind of tools that we have now that people in the Apollo era did not have, and this is just going to be so important as we move forward and actually implement future human exploration. I don't see any questions quite yet. Looks like there's someone who's typing. Here we go. Christine Hartzell at Caltech asks, have there been any publications on this tool?
Yes, there have. We've published on the comparison of the discrete element modeling of the wheel digging experiment, and we've also published on the scuff test results. And we're in the process of submitting a publication on the creation of the complex polyhedral particles using the regular polyhedral overlap method.
Okay, great.
And we also have quite a few. We also have quite a few presentations in the ASCE Earth and Space symposiums.
Yeah, if you wanted to send us a short list of those, we could potentially post that. We'd be happy to, just to make that generally available. Okay.
I think they are included in the overall project publications, but I can send those separately as well.
Okay, great, thanks. And I also wanted to say, Jerry, I really feel bad about those videos. I've seen those videos before, and they're outstanding. And I would be also happy if we can get working videos to put those up on the web. And for those who saw this talk and would like to see them, maybe they can just go to a site that we'll create. So if we can do that, what I will do is make sure that we put that on the forum website and announce it, and then maybe give people your email address if you have any questions. If they have any questions. Okay,
that'd be fine.
Great. So our apologies that didn't work. Let me see. We have a question. Let's see. Oh yeah, question from Otis Walton at Grainflow Dynamics Incorporated. Impressive capability. Will this code be available for others to use? And then it looks like someone already answered that. It will.
Right. I'll expand on that a little bit. Anton Kilchevsky is the primary coder for a lot of the CuPy work. Yes, our intention is that this code be available open source for non-commercial users, and we have a test user at Glenn, Alan Wilkinson. The difficulty is that we've been going through so many versions so fast and improvements that by the time we deliver one to a user, we're on to something else that user wants, and so it's we're moving almost too fast right now.
Yeah, okay. Great, all right, well with that, oh, I'm sorry, go ahead.
But what I was going to say is that we would be happy to work with selected users, because our concern with just a general distribution is we really don't have the capability to support the program right now in a general user environment.
Okay, all right, great. So with that, I'd like to close today's human exploration session. Thank all of the speakers, you, Jerry, as well as the rest. Very enlightening talks. Really enjoyed all of them today. And then I wanted to tell everyone online that we have an optional poster session right now for those authors who are still online. We'd like you to be by your poster in virtual space so you can answer questions real time for as long as you can, certainly no more than the next 45 minutes or so. And again, as I mentioned a couple of times earlier, we will also have asynchronous capability available on the posters if you have any other questions throughout the day and night. So thanks again, and we look forward to seeing all of you tomorrow morning Pacific time, 8:30. Thanks. Bye-bye.